As our newest and most perceptive eye on the ongoing unfolding of the cosmos, the James Webb Space Telescope is revealing many things that were previously unseen. From planets that rain sand to distant galaxies, James Webb is filling in a mysterious gap in our knowledge about the first 400 million years after the Big Bang, as well as providing clues to the existence of life forms elsewhere in the universe. However, note that James Webb has not only gathered striking infrared images, but also caused a few sags in the fabric of the Big Bang theory, questioning some of the facts we thought were well established. The Big Bang was an interesting event, but not the first event in the totality of reality. A recent shocking discovery made by James Webb has got the science community abuzz, as it not only could challenge the current standard model of our universe's evolution, but also break one of the fundamental laws of physics. The possibility that the Big Bang may be incorrect and that the universe might be larger and older than we think is a significant revelation. Looking out at our universe today, we not only see a huge variety of stars and galaxies both nearby and far away, but we also observe a curious relationship. The farther away a distant galaxy is, the faster it appears to move away from us. This continues as far as we've ever looked and remains true for all galaxies. The farther away they are, the greater their observed redshift corresponding to recession. In cosmic terms, the universe is expanding, with all the galaxies and clusters of galaxies getting more distant from one another over time. In the past, therefore, the universe was hotter, denser, and everything in it was closer together. Imagine what this means if the universe is and has always been expanding, not just for the future but for our cosmic past as well. If we extrapolate back as far as possible, we come to a time before the first galaxies formed, before the first stars ignited, before neutral atoms or atomic nuclei or even stable matter could exist. The earliest moment at which we can describe our universe as hot, dense, and uniformly full of stuff is known as the Big Bang. Some of you might read that last sentence and be confused. You might ask, isn't the Big Bang the birth of time and space? This is a view that many modern cosmologists can be sympathetic to. At one point in the history of cosmology, that's how the Big Bang was originally conceived. Take something that's expanding and of a certain size and age today, and you can go back to a time where it was arbitrarily small and dense, down to a single point where all the matter and energy in the universe comes together at once. That event corresponds to what we know as a singularity, a point from which space and time originally emerged. But we know that's not correct today. In fact, in 2023, there's a ton of evidence that points to a non-singular origin to our universe. We never achieved those arbitrarily high temperatures, there's a cutoff instead. Our universe is best described by an inflationary period that occurred prior to the Big Bang, and the Big Bang is the aftermath of what occurred at the end of inflation. Let's walk through what that looked like. During inflation, the universe was completely empty. No particles, no matter, no photons, just empty space itself. That empty space had a huge amount of energy in it at every location, with the exact amount of energy slightly fluctuating over time by about 1 part in 30,000 on average. As the universe inflates, expanding in a rapid, relentless fashion, those fluctuations get stretched to larger scales, while new small-scale fluctuations are created atop them. This superposition of fluctuations of small scales atop intermediate scales or atop large scales or atop superhorizon scales is one of the defining predictive features of cosmic inflation. This continues as long as inflation goes on, but inflation will come to an end, randomly and not in all locations at once. In fact, if you lived in an inflating universe, you'd likely experience a nearby region where inflation came to an end, while the space between you and it expanded exponentially. For a brief instant, you might even be able to detect what happens at the start of a Big Bang before that region disappeared entirely from view. In an initially relatively small region, perhaps no bigger than a human-sized hamster ball but perhaps much larger, the energy inherent to space gets converted into matter and radiation. The conversion process is relatively fast, taking approximately 10 to the power of 33 seconds or so, a brief amount of time but nonetheless not instantaneous. As the energy bound up in space itself gets converted into particles, antiparticles, photons, and more, the temperature starts to rapidly rise, from just a few degrees above absolute zero to perhaps about 10 to the power of 20 Kelvin over that same brief time interval. Because the amount of energy that gets converted is so large, everything will be moving close to the speed of light. All particles will behave as radiation, with so much kinetic energy inherent to them, regardless of whether they are massless or massive. Under these conditions, this conversion process is known as reheating and signifies when inflation comes to an end and the stage known as the hot Big Bang begins. In terms of the expansion speed, you'd witness a tremendous change from all prior behavior when the hot Big Bang first commences. In an inflationary universe, space expands exponentially, with more distant regions accelerating away relentlessly as time goes on. But when inflation ends, the universe reheats and the hot Big Bang starts. More distant regions will now recede from you more and more slowly as time goes on. From an outside perspective, the part of the universe where inflation ends sees the expansion rate drop, while the inflating regions surrounding it see no such drop. Under inflation, the distance to any object would double after a certain amount of time, and once that same amount of time elapses, the distance doubles yet again, and again, and again. The process is relentless. But once the Big Bang begins, all of that changes as the expanding universe immediately slows down once the first moment of expansion elapses. Probability-wise, it's extremely likely that from the perspective of whatever region of inflating space you're in prior to the Big Bang, you'll experience inflation ending in nearby regions many times. These locations where inflation ends will quickly fill with matter, antimatter, and radiation and expand more slowly than the still inflating regions do, leaving you in the inflating region as a typical region within spacetime, dominating its volume. These regions where hot Big Bangs occur will expand away from all the other locations where inflation still goes on exponentially, meaning they will very quickly recede from one another's view. In the standard inflationary picture, because of this expansion rate change, there's virtually no chance that any two universes where separate hot Big Bangs occur will ever collide or interact. Finally, the region where we will come to live gets cosmically lucky, and inflation comes to an end for us. The energy that was inherent to space itself gets converted to a hot, dense, and almost uniform sea of particles. The only imperfections and departures from uniformity correspond to the quantum fluctuations that existed and were stretched across the universe during inflation. The positive energy quantum fluctuations will correspond to initially overdense regions, while the negative energy fluctuations get converted into initially underdense regions. The typical difference might only be at the 0.3% level, but that's still enough to serve as the eventual seeds of cosmic structure. We cannot observe these density fluctuations today as they were when the universe first underwent the hot Big Bang. There are no visual signatures we can access from that early on. The first one we've ever accessed comes from 380,000 years later after they've undergone countless interactions. Even at that point, we can extrapolate back what the initial density fluctuations were and find something extremely consistent with the story of cosmic inflation. The temperature fluctuations imprinted on the first picture of the universe, the cosmic microwave background, give us information on how the Big Bang began. What might someday be observable to us, however, are the gravitational waves left over from the end of inflation and the start of the hot Big Bang. These gravitational waves move at the speed of light in all directions, but unlike the visual signatures, no interactions ever slow them down. They will wash over us, arriving continuously from all directions, passing through our bodies and our detectors. All we need to do if we want to understand how our universe got its start is find a way to observe these waves, either directly or indirectly. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.